Hi guys, welcome back here at DEC Engineering Tutorials. So this time, continue tayo sa design of drainage channel. So this is part 2. Okay, so last time I have shown you this a little bit here. So na-stop tayo dun sa uniform and non-uniform flow, no? So continue lang natin yung discussion natin. For a while. Non-uniform flow. Okay, so dito tayo, no? Derivation of CHEZY'S formula. Okay, so and considering this section 1 and 2, we have this channel bed whose slope is SO. Then we have this horizontal line. So we have this normal depth to hydraulic gradient line, and we have this energy gradient line, and we have this velocity coming from upstream down to downstream. So if you consider this diagram here, so say we have this channel reach L. So we have these forces F1 at section 1, and then F2, no? This hydrostatic force at section 2. And then aside to that, we have also this parang fractional force, no? The shearing stress. Okay, tau O. Okay, so that one. Considering the cross-sectional area of our channel, we have this cross-sectional area, and then we have also this weighted perimeter P. So meaning, yung shearing stress natin is we have this tau O times perimeter times the length ng channel natin. And considering yung water that passed through section 1 and 2, so we have this weight, we have density multiplied by the cross-sectional area times the length, no? But we are concerned with the forces along sa direction ng flow natin, no? So if we assume this is theta, so again, this is also theta, no? Thus, we have these forces here, W sine theta. Or we have this density multiplied by area times length sine theta. Okay, so according to force balance along the direction ng flow natin, we can write yung ganito, no? We have F1 minus F2 plus the W sine theta is equal nung shearing force natin. Cancel out yung F1 tsaka F2, na? Kasi same lang yan sila eh. So, bali yung matitira is ito na lang, no? So, ngayon, if we simplify that term, so we have this shearing stress which is equal to density R sine theta. So, for channels with slope that is less than 0.1, we can simply assume that SO is equal sa SW, which is approximately the slope, which is also equal to sine theta. Thus, so pwede natin sabihin na yung shearing stress is also the density times the hydraulic radius times SO. So that's the shearing stress. So again, simplifying that one, so we have this formula from CHEZY. Yung C dito is the CHEZY'S constant, whose value depend upon the type ng channel surface natin. So this is a French bridge, an hydraulic expert, and the 90 Chezy, 1718 to 1798. So nagpropose siya ng itong formula, which is velocity. The average flow velocity is equal to Chezy's constant, square root of the hydraulic radius times the channel bed slope, SO. So, aside from Chezy, meron din tayong mga empirical relation. If you say empirical, meaning derived from laboratory, no? So, ito yan sila, no? Si Bayesian formula, meron siyang ganitong formula. C is just 157.6 over 181 plus K over square root of R. So, yung value ng K depends upon the type ng channel surface, no? So, we have this different channel surface and we have the corresponding Bayesian constant for that channel surface, no? Aside from Bayesian, meron din tayong cutter, no? Okay, so ito yung formula niya in British gravitational unit or English units, and we have also these SI units, no? Ito yung mga formulas nila. So medyo mahaba siya. Anyway, yung makikita mo dito, meron tayong N na makikita sa formula nila, which stands for Manning's roughness coefficient. Meron din tayong S, which stands for slope, and we have also this R, which stands for hydraulic radius. Aside from cutter, we have this Manning formula, no? Again, another empirical radiation shift, which is constant. That is just 1 over n multiplied by r raised to the power of 1 over 6. So if we simplify this, if we substitute this one dun sa formula ni Chezy, so we can derive this formula, which is commonly used sa channel design, no? V is just 1 over n, r 2/3, s 1/2. So this is for SI units. So this become 1.486 for English units. So the value of n depends upon the nature of channel. So we have also this canal density and capacity. Canal density is approximately 50 to 75 hectares for every kilometer of canal. So yung capacity of canal shall be based on the area, the water requirement, the distribution and farm losses, and also the conveyance losses in canal. So we have these design requirements. So the following parameters shall be determined in order to design an open channel. So these are, we have here the design discharge or the flow velocity. We have this, flow capacity, and then we have flow velocity. The third parameter is the roughness coefficient. The fourth is the bottom slope, no, or the channel bed. The pre-board, the canal cross section. Okay, so let's talk about the flow rate or the discharge or the flow capacity. So meron tayong dalawang formula. So we have this Chezy equation and Manning's equation, both for SI and British gravitational unit, no? So we have this formula. So makikita mo dito sa English or BG units, it becomes 1.486 over n, AR 2/3, S 1/2. Anyway, yung flow kasi dito is just area times velocity. Kaya naging ganito yung formula. We have this area times velocity, and we have this area times velocity. Continuity equation. Flow velocity, so for unlined channels, the design flow velocity of the canal shall not exceed the maximum permissible velocity in order to avoid destructive erosion to the channel and progressively destroy the fertile lines, no? So the maximum permissible velocity depends on the resistance to erosion of the banks of the canal. So these are the maximum velocity for different types of materials taken from Irrigation Engineering Manual for Diversified Cropping in 1991. So this different type of materials, and we have the corresponding maximum permissible velocity. Permissible meaning yung parang allowable niya, no? So bali dito naka-meter per second siya, no? So you can also use that one in the stability design, no? For line channels, the minimum permissible velocity shall be considered, no? However, the flow velocity shall be innocuous, too low to produce sand deposits or allow weed growth inside the canal. The permissible minimum velocity can be estimated as 0.6 meter per second for plain water and 0.9 meters per second for water with sediments. So the idea is to have a stable channel. So irrigation channels should be stable, having negligible scar and negligible deposition of sediments. Obtaining a low velocity requires an increase in area for scarring to be eliminated. However, large canals are costly. So recommendation on limiting velocity together with the corresponding value of roughness N are shown in the table 3. The values shown applied to water depth of 1 meter or less in canals that have been brought to capacity gradually. So for the depth of canal over 1 meter, so bali kung greater than 1 meter, the velocity should be increased by 0.15 meter per second. For canals with sinus alignment, a reduction of the velocity should be increased 0.15 meter per second. And for canals with mga sinus alignment, no, meron siyang parang meandering effect, a reduction of 25% is also recommended. So ito yung table 3, no? The limiting velocity for essentially straight canal after aging. So we have these for straight canal after aging. We have these different materials and we have this value of coefficient channel roughness and kang Manning, and we have also this velocity in meter per second for clear water and for water transporting colloidal salts. Okay, another parameter is we have this roughness coefficient. So the value of roughness coefficient shall not be based on the degree of the original finish, but on the surface that will exist after a few years of operation. So normally, earth canals shall have a velocity range of 0.3 meter per second to 1 meter per second. So ito yung permissible velocity, again, depending on type of material and permissible velocity. So the side slope of the channel. So for channels excavated in clay, we have 1:1 in cutting and 1:1.5 in fill. No? So for channels in GIS, soft rock and hard rock taken respectively as 1:0.5, 1:0.25, and 1:0.125. And in hard rock, the sides may keep vertical. So values of roughness coefficient of different materials forming channel are shown also below. So this is another source, no? So ito yung mga mean roughness coefficient for different strata and condition of the channel. So we have these natural channels and we have their corresponding roughness coefficient for natural channels, for excavated or rigid canal. We have ayan, no? Earth curve and irrigation section, dragline excavation or rigid, rock excavation. So meron din tayong mga roughness coefficient nila. For line canal, we have rigid, gravel riprap, rock riprap. Ayan, no? Meron din tayong mga roughness coefficient. So, yung source nito is Irrigation Engineering Manual for Diversified Cropping in 1991. So, ito naman yung Horton values of N. Okay? Yung roughness coefficient N to be used with Cutter and Manning's formula. So, we have these different surface. Ayan, makikita mo yan. And we have these different N values. We have best N, good N, fair N, and bad N. Okay. So, depende kung anong surface yung ginamit mo sa design mo. So, these are the values commonly used in designing. So, this is taken from King HV Handbook of Hydraulics. Publisher is McGraw-Hill, 1938. Okay, so another parameter is side slope, no? Or the Z. So, yung side slope na yan, ito yan, no? Ayan, yung Z na nakikita nyo. We call it side slope. For line channels, the recommended side slope is 1.5:1. And for unlined channel, side slope shall depend on the soil characteristic and should be flat enough to avoid the possibility of caving in after saturation. Steeper slopes can be permitted in cutting ridges in rock or hard strata but not for embankment ridges. Earth canals are generally constructed trapezoidal in shape with side slopes determined from experience and stability studies of the bank material. So yung side slope na 1.5:1 have been found adequate for most earth materials. So this slope may however be stiffened if soil condition so warrants. So for rock or hard pan na materials, yung side lobe na recommended is 1/4:1 or 1/2:1 may be used. Initially, yung mga hard materials but subsequently would become unstable like shell because of its physical property of being easily pulverized or disintegrated after exposed to the elements should be provided with flatter side slope which is 1:1, no? And then with provided with concrete lining if necessary, no? So may mga hard rock kasi na parang kung medyo exposed na napopulverize siya, no? Okay, so if during construction it has been found out that the shearing strength of the soil becomes so weak when it is saturated and continuously sliding down of the side slope cannot be checked, then it may be necessary in this case to construct a closed conduit or cut and cover section. So the side slope depend primarily on the engineering properties of the materials through which the channel is excavated. So very masabtan lang siya. So ito yung mga recommended na side slope for unlined channels. So for different location or strata, and we have this side slope, no? Horizontal is to vertical, no? We have these cutting ridges, embankment ridges. So yung source nito is design of manual on irrigation facilities. So another table we can also use is ito, no? Depende kung ano yung material. So meron din siyang side slope, no? So we have also channel bed width and depth ratio or the BD ratio, or we simply equate this one into M, no? Yung M na ginagamit natin sa formula. So for line and unlined channel, several B over D ratio can be selected in order to satisfy a given design discharge. So we have this channel discharge, naka cubic meter per second siya. So ayan, no? So ito yung gagamitin mo na M, which is equal to B over D. So meron kang mga values dito for unlined channel and for line channel. So yung source nito is design manual on irrigation facilities. So for bed width and channel depth, ito naman yung formula. We have the discharge multiplied by the roughness coefficient all over the bed slope raised to the power of 1/2 is equal to the cross-sectional area raised to the power of 5/3 over the weighted perimeter raised to the power of 2/3. So yun yung formula natin. So another parameter in channel design is the channel slope, SO, or the bed slope. So the bottom slope or the slope of the channel bed shall be determined from the topographic survey. So bali ito yan. Yan, yung SO yan yung channel slope. Okay? So we have these different types of slope. We have the mild slope. So pag yung SO natin is less than the critical slope, or yung YN natin is the normal depth is greater than the critical depth. So meaning mild slope. We have also this steep slope. So pag yung SO natin is greater than the critical slope, or yung normal depth natin is less than nung critical depth, no? So meaning steep slope yun, no? So ano yun? Super critical, no? Ang flow. And critical slope is pag equal yung SO and SC, or equal yung YN at saka YC. Mild slope. And we have this horizontal, no? Pag yung slope is 0, no? Meaning flat siya. And YN is approaches to infinity. Okay? Okay, so we have also this GBF classification. So this is applicable for non-uniform flow sa channel natin, no? So sa GBF classification, we have this, for instance, S1 is not equal to S2. So, okay, so I think I leave this one in the next video na lang, no? Kasi mahaba to no? So we have this GVF classification, and then after this one is we have this GVF analysis, no? And we have also the RBF analysis. Okay, so I think that would be part 3, no? Sa video na to. Okay, so keep on watching and keep on learning. See you in the next video. Thank you.